So the next topic have to deal with kind of lying with graphics, visualizations being not perfect, and maybe sometimes either confusing or completely distracting. Sometimes it's done on purpose, other times just so happens that it turns out like that. So I have this paper here. It's kind of in the red down here if you're interested more detail. That's where I took it from. But it's called visualization mirages, and so they have a kind of longer definition. I'll put all of it on the slide, but the idea is that the message, if you spend a little bit of time on the visualization, not entirely studying everything in some cases, that examination, if you look at the data and actually analyze it for a while, you realize those two are not connected. One is misleading somehow. And I was telling you that we will run into this again. It's the slide that kind of says where the data, we get the data, we process it. We get raw data, we process it. We prepare it somehow, then we create an image and encoding of it. So we can create some graphics, and then we navigate through that graphics. Kind of the same thing. And it can happen at each and every step that we do something that will create a visualization that is not entirely, and again, it's probably not a true false. It's just there's levels. It's going to be further from what the data really is, what other people would think that data is about. So here are some examples. So one of them is the same visualization, which you see right here at the bottom, applies to all of these data sets, all 4 of them. So on this one, there's only 2 points, so the data is really sparse. I have, an X and a Y, or A and a B, I think, on the, sorry, the way they use it is left and right. Because X is normally an axis, but here is a data set. I have data set X and a data set Y. And it's only 2 points, and the visualization looks like that. On B, notice that the Y is actually a lot lower. Most of the Y's are lower than X, or at least as much as X. But there is an outlier here. When we aggregate data and only show 2 bars, they look the same. Over here, they are pretty much the same, but in this particular point, there's a lot. There may be 100 of them stacked on top of each other. So when I display that point, like dot after dot after dot, and that's why visualization looks the same bar here. Once I aggregate that left. And this one, the difference is that here I only have 2 points. Here I have a lot of points kind of in the middle, and they still look like that. So if I visualize something that's 2 and some that's 100 data points, it's hard to compare them. It may be not, that's kind of inviting trouble. And here is another example of a mirage like that.
They're representing the below one?
I think, yeah, that's true. So A, representation of A is the blue bar charts. The representation of B is also the blue bar charts. The representation of C, also the blue bar charts. And then D also. If you take it and you plug it into a visualization tool, that's what you're going to get. If you only use 1 bar chart, 1 bar for X and 1 bar for Y. That's kind of where we're going. So you're basically aggregating everything that's in X and everything that's in Y. You do an aggregation and put it there.
The sum of all 4, the below one is the sum of all 4, or is each one?
Each one is exactly the same. So it's not the sum of all 4. Each one, if you represent it, you get exactly the same result. Exactly the same 2 bars, X and Y. So that's why it's a mirage, because you're not seeing the underlying data. You're seeing those bars, and it might give you the wrong idea of what the data is. Here's another example they have here is power consumption. And it's broken down by years. You can kind of see it here. And can I give some detail about B-plot? Well, B-plot has an outlier. And if you look at most of the data in Y, I'm sorry, most of the data in Y is below the data, is smaller than or at least equal to the data in X. But because of this outlier, you get exactly the same representation that tells you X is bigger, Y is bigger than X, which is not what is really happening there. Okay, so in other words, how do I do this? If I take this and I build a visualization for it, a bar chart, I'm going to get this result. If I take this and I build a bar chart, so this only has 2 data points. It's easy. This one has many data points. I don't know exactly the detail, but if you want, I can tell 10 each. And I get exactly the same representation. If I take this data set, where you can see the X and Y are pretty much the same, but then there's a lot more X's that hit the top here, I get exactly the same result. And if I take this data set, I get exactly the same thing. So obviously, you can see the underlying data in a different representation. And you can see that the bar chart itself, so what the user will see, the user only sees this part. They don't know which of the 4 is being represented, because so that's kind of the thing about mirages. It's a mirage. It's something you think it's there, but it's not necessarily there. Another example of the mirage is going to be this part of the visual. So we're moving on to the right side. What you see is power consumption over the years. It's broken down by year. And it's OECD countries versus non-OECD countries. But here's the catch. There are a bunch of null entries. So it's not one entry for a year. It's like every month, maybe. For some months, there are nulls. And if you look at the nulls, which is B here, the B part of the picture, you can see that 2012 has a lot more nulls. So data was not reported, it was lost. Something happened in 2012. And therefore, if you do a sum, so at the top here it's a sum, because I have so many nulls, it looks like the consumption went down in 2012. And now, if I know that, I would go ahead and say, no. What if I do an average then? That would take care of the nulls, because you can see there's probably a lot more entries in these years here than in 2012. Lots of nulls. So if I do an average, I end up with this visualization, and it says that consumption is going up. That's not true either. That's the funny part. I mean, it's not entirely true. So I do an average. Why is it not true? Look at the C part. So here, you can see that OECD countries consume more than double energy than non-OECD countries. But however, in the year 2012, which is this graph here, again, nulls, how many nulls do I have? I have all nulls on non-OECD. So all the countries that don't consume a lot, they didn't report. The countries that reported, so the countries that reported are the missing part here, the non-nulls. Are all of them OECD? So even if I do average, it's going to show higher than usual, but I don't have any entry from the lower consumption countries. So both of them are mirages, because that's not what the data says. What should I do? Maybe get rid of the year 2012 altogether. I look at it separately. I cannot put it in there. Just again, because the way this works. And notice this one here also kind of shows there's a lot of nulls, which gets maybe go down a little. Okay, so you have to look at the data. Like I said, the whole process, it's not just the visualization part. Do reasonable people will agree that consumption goes down? No. Will they agree that consumption goes up? No. It's like, I don't know. I don't have enough data, basically. So these are two examples of, that's kind of how the paper starts. I'm going to move on to the next one. Here is another example about these mirages. They were doing at energy usage versus life expectancy. So life expectancy, this is the year, and the energy usage versus life expectancy. So you can see energy usage is going to be this color. Life expectancy is going to be this color here. And by looking at it and doing an aggregation on it, and it's not always the aggregation, like sometimes, I mean, a lot of times that creates problems. Dropping null records, replace, anyway. But with that, it shows like, yes, energy consumption increased, life expectancy increased. However, if you look at the actual energy usage by country, you can see that most countries didn't increase that much. It's just China and US are the most with the power. So they really determine the shape of the yellow line there. On top of that, to be worse, this one starts at 55. The axis on the life expectancy starts at 55. If it would start at 0, that line would flatten. So really for the period, it was a negligible increase in life expectancy. And the energy usage was mostly due to these two countries. Okay, let me see what this is about. I need to zoom in a bit. Data curation can cause errors. So here's the mirage. If I look at sales, so I think this is sales by A versus B. And I have a case-sensitive filter. Yes, A and B, it's this much, but notice that there's probably a misspelling. Somebody entered A lowercase. And there's quite a lot of sales by A lowercase. So if it's a data curation, if data quality issue, that also leads to visualization. Then actually A sold a lot more than B in this case. So you want to encourage that. So it's how you do the search. Another one here. Again, I need to zoom in a bit. And the context is mainly the kind of the what's another view of the data. If you notice here for the Q4 of 2010, which is this one, there is really no data collected. You can see the data represented as points. So in the magenta shaded area, there's no data. So the Q4 really shouldn't have any data. So the fact that it's slower doesn't mean much because there is no data. It gives the impression we're down, but they weren't. It's just I don't have enough data about it. All the data points, you can see them represented here that were used for aggregation. Another one here. This has to deal with scale. So this is 100-meter dash world record over the years. And you can see that people are getting faster. But here they're exaggerating. They start at 9.6 seconds rather than at 0. So if you start at 9.6, it looks like it's a big improvement. But it's only about 1 second improve from 9.6 to from 10.6 to 9.6. So the scale can be deceptive. What's the best scale? It's also an issue. Sometimes you don't want to start at 0. Right here, if I start at 0, I won't be able to see these because they're all kind of grouped together there. So I might, if I want to look at other countries than China and the US, I might as well just take them out of the, and resize the whole thing. See what's going on. If I'm interested in China and the US, yes, I can start my axis right there because they're not below that. And another one here, it's just basically what data is being considered. So they look at crime data generated by 911 calls on one side, and note that most data kind of fall where it falls. I think that's maybe Manhattan. And here is the data including white collar crimes. And obviously, if you're a stock market broker and you defraud somebody, nobody's going to call 911 and say, hey, I lost $3 million today. So if you add those, it kind of changes. So it's basically your data source problem right here where you take and compare. So knowing what your problem is and knowing where your data source is. Some of the things they suggest to do, so those are examples of where it can come up. And they kind of have more or less two solutions, well, three solutions. One of them is here they're saying precipitation in various, but the idea here is that for May, over the years, so this is for a number of years in May, what they do is they lay down the same axis. So here there may be a smaller one, but you can't see it because you only see the maximum because it's laid on top of them. So one solution they had is use transparency. And you can actually see that July is a lot lower than what it looks here. And maybe June is not. So each bar is semi-transparent. So if you put on top of them, if you see a big fuzzy thing, it means there's a big variation. Some of them are really small, then you have medium, then you have a little bit taller, and then you have maximum right there. So that's how, using transparency smartly, it can give you an idea of the bars that are on top of each other. So that's one solution. Second solution, change the order of the data. So this one shows, let's see what, world indicator data set. So something world health, expense, percent GDP, and life expectancy. There's a lot of countries plotted on top of each other. So what they do is, and that's done by the computer, really a human won't be able to do that. They plot the same data, but use, so if you plot it, the first country, I don't know, Afghanistan, gets a dot. And then by the time you get to the United States, that gets a dot that may be on top of Afghanistan right there, or partly covering it. So as you plot it in that order, you get things that get covered by others. So one solution would be to change the order, replot, and see how safe is your data. So kind of that is their theory. How robust is your representation to changes, to shuffling it? So they replot everything, and then the computer computes the difference. And you can see that right in the middle of the blob, there's a lot of differences if you plot them in a different order. So that means they're sitting on top of each other. So it may not be the best representation for that at that point. So it tells you that the visualization is not very robust if I make permutations in how I display the data. Overall, the theory is, if you make small changes to the data, you should see small changes in visualization. If you make big changes, you should see big changes. I'm not sure if necessarily they go with big, but you can do small changes. Does the visualization change a lot or not? And the other thing here is, rather than changing the order, you sample different things. Going back to the beginning, this is the beginning picture right here. Remember, we had a discussion on it. So not this one, this one. If you remember this one, Here I only have 2 data points. Here I may have 10, 15. Here I may have, 20, 30. The idea that they have is, what if I randomly sample the data and I come up with, and I use the same encoding to represent that data set? Would I see a lot of variation in my data? And to do that, what they do is they sample it once and they come up with a bar chart. But they also use a little bit of this idea. They don't put the bar chart completely opaque. They have it semi-transparent. So in here, you can see for the data set A, there's only 2 points. No matter how you sample it, you get the same thing. And then on the passes, basically each of the pictures, does it show the relationship, the fact that X is smaller than Y? Is it true or not? Do you end up with a visualization with a bar chart that still shows that X is smaller than Y? And you can see here it's completely flat. So all of them show the same. There's no other way to do it. In this example, you notice it starts to get a little bit fuzzy. Sometimes the bars get a little bit taller than the median, but it's not that bad. None of them are bad. So the relationship still, no matter how you sample, or at least in the trials that they do, almost nothing. Well, maybe there is a little bit of a shade of things not being passed. You can see that sometimes X is slightly bigger than Y. Very vaguely right there. Here is completely missing. Here there's a little bit of brown. And then you can still see some fuzzy stuff. So there is a little bit of variation depending on how you sample. For this one here, there's quite a lot of variation, and you can see there's quite a lot of them when you see the opposite relationship than on the positive. Especially the second one, kind of see how higher it gets here. And then on this one that has only 2 here, and then a lot of the sample data is in there, you kind of see it's maybe not as it gets almost equal with the fuzziness included. And then there's about as many situations in which Y is larger as X being larger, right there. Okay, so some of them you can actually do yourself by, I'm not sure if this last one, well, I think you can probably do all of these more or less yourself using the tools that you have, and maybe a little bit of programming on this side. You can kind of select your data. So this may require more work, a little bit of Python to just get randomly distributed data, and then have a pipe where you place that data on a graph. So you can create new data sets. So in other words, remember that a data set is a bunch of rows in a table. Well, you just keep adding rows to it. When you sample, you add more rows. You sample one more time, add more rows. Sample one more time, add more rows. And then when you build a visualization, make sure you put them on top of each other. So add maybe another column that said sample number 1, sample number 2, sample number 3. And then you could probably almost simulate it for any data set that you have. But probably this requires more programming. This definitely requires programming. I'm not sure how I would do it without having access to the maybe I export the data as a JPEG or something and then do it. It's going to be harder though. This one can be done kind of the same way. All I have to do is turn the transparency on. So this is almost automatic. Most tools should allow you to check for something like that. This will require lots of programming because you have to check pixel by pixel. And this is semi. If you only want to sample it 5 times, then you can do it manually. Take the original data set, sample it 5 times, sample it 1, 2, 3, 4, 5 times, and then display everything back on the same picture. Also in the, actually, I'm going to stop.